guys. I'm really tired, so I gotta go a little slow with this. We got a wedge cut from the cardioid cylinder. R equals 1 plus cosine of theta. So here's the x-axis, here's the y-axis, here's the z-axis. And if I look at that cardioid, I think it's basically doing this. Can you guys be honest with me? Is that clear? Just be honest. Because you want me to sketch it by hand, I will. I just in my head, I can see it that way. Oh shoot, I made a mistake. You know what? That's a cardioid sketch in the xy coordinate plane. We're really talking about a cylinder. So it's really going up like this, isn't it? And down. Oh shoot, I'm not done. We've also got a plane located at z equals 2 minus x. Sorry, I have no idea what that looks like. Z equals 2 minus x? What was that?
Y can be anything.
Yeah, I know. I'm just trying to sketch the plane. If z equals 2, that means the x-intercept is 2, the z-intercept is 2. Okay, I've got it. So it's this plane right here. Brad, so far so good?
Yeah.
I think the other wedge has the equation z equals x minus 2, but that means the z-intercept's negative, the x-intercept's positive. I think it's just like this plane, but projected straight through the xy coordinate plane. I think it opens downwards like this. And then scooting off in this direction.
Well,
Yes.
Let's say we can't draw and not draw that.
Yeah, this is just a nightmare to draw.
Like we have to draw it in order to see it. Give us a picture.
Some of these ones are
All right, how about doing this,
really
guys?
just
I think because of all the symmetry, to make your life easier, let's not do it. Let's just talk about the wedge I make with the xy coordinate plane with the plane up top. And so I think that being the case, here's my corresponding surface in 3 space. Looks something like that. It's a little wedge that looks like this.
Chuck was doing something with these the other day where he was just drawing, the XY axis and then, just kind of visualizing where it's going to go with the Z axis. It seemed a bit easier.
Well, I don't know, it's not that bad.
Okay.
I mean, the bottom line is it looks something
Yeah.
like this.
It's a slice of pizza shaped like a cardioid.
Exactly,
right?
but it goes into a point.
But you don't have the cardioid on the edge.
I know,
Right.
so my boundary doesn't look like cardio, but it's easy to draw. And keep in mind, I only have half of it, because I've got to duplicate that downstairs. You guys, I haven't even read you the question. I haven't read it myself. I was just considering that shape, I have no idea what I'm trying to do with it. So, question. Choose the best coordinate system and find the volume of that solid. Surfaces are specified using the coordinates that give the simplest description, but the simplest integration may be with respect to a different variable. Gotcha. Well, you guys, I don't know. When I take a look at that shape in the xy coordinate plane, it's a cardioid. It just screams out that polar coordinates. It's already expressed in terms of polar coordinates. It's just maybe the way to go is to use cylindrical coordinates. And to use cylindrical coordinates and using a triple integral, I think the volume is going to be expressed in the following fashion. What's the integral position? I can't hear you. I can't hear you. R. Isn't it?
Mm-hmm.
Oh, then my order of integration is going to be respect to, then respect to, most likely, then respect to theta.
Didn't you say it's always going to be that in pretty much every case that we see?
I'm nervous about saying all. I mean, if Z, R, and theta,
I said every case that we see.
I suppose I can ask you this. If R and Z and theta are constants, it doesn't matter what the order is. Do you think I'd ask you a question where R, Z, and theta are constants?
Yeah, no.
No. So let's talk about how the Z's are changing. Well, everybody, with my green pen, if I draw an arrow emanating from the origin and going out to the surface, emanating from the origin, like that. we talk about extreme values? Why are you shaking your head?
When you're doing spherical.
Yeah, you guys, this is thinking of, or this is using spherical coordinates, where I'm looking at how rows change. If I'm gonna integrate respect to z first, isn't that more straightforwardly just an upwards arrow within this particular region in 3 space? Now, as I slide this arrow around where its initial point is sliding up everywhere in the interior of the cardioid, I think
it's
the
just
initial z value is gonna be
0.
0. The terminating z value is gonna be on that plane.
1 plus cosine
Are
of
you
theta.
using symmetry?
Yes, I am.
Okay.
So, like I said, I'm only gonna look at what's above the xy
Okay.
coordinate plane. So I think my z values are gonna range from, can you guys help me, 0 to, I don't know where, was it 2
To-
minus x?
They have to put that, they have to put.
Yeah, it's 2 minus r cosine theta.
Thank you, I didn't even catch that yet. Technically speaking, is if I'm gonna generate this triple integral using cylindrical coordinates, I gotta convert the x to r's and or thetas, and x is indeed equal to nothing more than r times the cosine of theta. Next, I do think when it comes to the r values, well, you guys, isn't that now an issue of going back down in the xy coordinate plane? No tricks this time. With my, okay, I'm only in green, with my green pen. Allowing the r values to be emanating from the origin, going to the outer boundary of that cardioid in any direction. I think any of those arrows have an initial r value of. But a terminal r value on the cardioid, so I think my lower upper bounds of integration are going to be 0, and I've lost the rest. Was it 1 plus? And finally, I think my theta values are going to range from
0 to 2.
0 to 2 pi. You guys look at this. No tricks. I really did make another mistake. Remember how I said we're going to exploit symmetry? I really should have had 2 elements. What if I chose not to use symmetry? What if I chose this to be a positive 1? How would the theta values change?
It'd
Oh,
be-
they wouldn't. How would the r values change? Oh, they would. But I think the z values would go from,
The lower plane.
yeah, that lower plane, which I can't read, is it x minus 2?
Yeah.
So wouldn't that be a r cosine theta minus 2 down here instead of 0? It'd give you the same answer. Brad, you happier?
Yeah.
Eric, would it make our lives easier when we're doing this to convert all of the r's to 1 plus cosine thetas? I mean, because we're stating it right there, and that way we only have variable. Would that work?
This right here is really going to be a bound for the r variable. So if you're going to anti-differentiate, well, I guess in this example, if you're anti-differentiate by z, that's not going to have any effect. It's up to you. It works.
So it's the same, like just because you know r equals 1 plus cosine theta over there, you can replace it there?
I do think it would create a lot of work, because once I anti-differentiate by z, I've got cosines. And now you're going to have cosine squareds. These are double line identities. So I just think it's a lot of work.
Oh, okay.
You guys, it is time to change the name of the game.
It's time to do something.
Well, maybe just temporarily. I'm still going to be using all these tools. But you guys check this out. Here's a river.
Which chapter are we in right here?
I have no idea.
Please don't say, oh, okay,
14. Is that
14.1, vector fields? All right.
So you guys, check this pretty picture out. I've got a red pen. I want you to take a peek at this river. See what happens when it comes to the water flow. Now let all these arrows represent velocities at given points on the surface of the water. And it might look something like this. I'm trying to create a pretty picture in which I've got a lot of vectors associated with points on the surface of this water. Again, my red vectors are velocity vectors.
Is it going to be the exact opposite?
Beautiful. I think I'm 100% wrong. Because I think if these red arrows are going to be vectors, I think their magnitudes should be really large, where I've got this river pinched, because I think the current's going to be stronger, the force is going to be greater. I think the velocity of a particle in the water is going to be much greater. So I think everything in my picture is completely backwards. However, a vector field is just this, associated with every point in the plane, or maybe through space, a vector. Hence title vector field. If I had a vector field described by this equation, how about a vector field? I'll call it F. Eval at x comma y. Be equal to, well, let me just put it in vector form. How about something like this? You guys, I'm sorry, it's a very simple vector field. I might also represent it this way. X times I bar plus y times j bar, just using my unit vector notation. But you guys, it's something really off with my notation. Just really is going to be a vector value function. I insist I'm going to have to use a bar notation. Now, the author of your text does not. He can get away with using boldface letters because they're easy for him to print. I just can't do that. So I'll use my bars instead of boldface. Let's talk about what this vector field looks like. Here's the x-axis. Here's the y-axis. I think I'm looking at a vector field, which is nothing more than a collection of vectors associated with the points in the plane. For example, look at the point 1, 1. What would the corresponding vector associated with that point look like? Anybody? So it's going to be arrow that has magnitude square root of 2, going in the direction of 1, 1. I think when it comes to the vector associated with this point right here, 1, 0, what would this vector look like? 1, 0. Yeah. I didn't look like that. How about the vector, oh, did I just get myself? Associated with the point 1, 2. What would that look like?
Root 5, oh, magnitude of root 5.
Magnitude bigger than 1. Something like that. But going in the direction of 1, 2. And I think if I were down here, I don't know, I'll choose another point like, how about 1, negative 3? Well, what does associated vector look like? 1 to the right, and then 3 down. I think it looks sort of like this. Even greater magnitude. Do you guys mind if I'd be really lazy now? I think more totally speaking, here's what's happening. It's just the further I get away from the origin, the longer the vectors are. Do you guys agree with me, loosely speaking, now that I'm not being very careful? And again, I think this, what can I call this? This radial vector field has all the arrows leaping away from the origin, whose magnitude is getting larger and larger as it leaps further away. What do you think this vector field would look like if I did this? Let's suppose it's still a radial vector field, but all these vectors have the same magnitude. Very nice. I think such a vector field like this, all the vectors have the same magnitude, is going to look just like the example I had in my first. F bar eval of x comma y is going to be a vector of the form x comma y. So just divide out by the magnitude of each and every one of those vectors. Oh, by the way, you guys, I skipped something. In both these examples, my first and second examples, what is the associated vector at the origin? You have the 0 vector, which has magnitude 0, but direction of? Yeah, how about no direction? It doesn't really have a direction, so it's that 0 vector. What do you think this would look like? Sorry, guys, I'm just thinking. Any thoughts?
Infinitely along in the z-axis.
I'm sorry, say
Infinitely along the z-axis.
so all the vectors are parallel to the z-axis.
Yeah.
And what can you say about the magnitudes? You get further and further above the z-axis. Further and further you get above the xy coordinate plane. Their magnitudes are larger and larger and larger. I think maybe in the x, y, z coordinate system, I just got a bunch of vectors looking like this. Emanating from the xy coordinate plane. Oh, sorry, I made a mistake, didn't I? Actually, if I've got a point on the xy coordinate plane, what do the vectors look like? Yeah, they have zero magnitude. I don't see them. But the further and further I get above the XY coordinate plane, the greater the magnitudes. Did you guys see that? So in 3 space, I just got a bunch of vectors opening in an upward direction. So in the XYZ coordinate system, I just got a bunch of vectors going in the upward direction. I can say a third time.
Could they go negative down too?
When would they do that?
If Z is a negative?
Thank you. So I think for any point below the XY coordinate plane, I guess I'm wrong. I think those vectors are going to be opening in the downward direction. Of course, the further down they are, the greater the magnitudes. Just the opposite direction than I had before.
Doesn't it, I guess by the way you're drawing that picture, it makes me think that there is a Y and an X amount, like a Y and an X value in the drawing that you're making. Wouldn't they all have to be just on the Z line?
See, I disagree. I think you're right. I think with all these vectors, there are X and Y components to them in terms of the location of the initial point of the vector. It's just the X and Y coordinates have no determination in terms of the direction and magnitude of the vector. So I think the X and Y coordinates of all the points in free space are important for the location of these red vectors. They just have no impact on both the direction and magnitude of these vectors. At least with the one I made up out of thin air, and I know it's a silly one.
Yeah, but that says it's at 0, 0 on the XY plane, and then you just go up and down.
Well, careful. I said if I'm on the XY coordinate plane, there is no associated vector. They're all zero vectors.
So you're just like going levels up.
Yeah, I'm looking at planes going further and further above the XY coordinate plane, but parallel to the XY coordinate plane, and any vector starting on a point on a plane is going to have the same magnitude. You guys, I know I can't draw. That's difficult to draw in 3 space. And actually, I take that back. I think it's difficult to draw in 2 space. So a lot of times I cheat and exploit technology.
If we could do that fast.
Well, you guys, on an exam, I'm not going to be wasting your time saying, oh, plot this vector field. Besides, I think what's most important for you and I is to be able to talk about, I don't know, moving within vector fields, talking about how much work is involved if I've got a structure like this or a vector field like this, and I want to talk about, I don't know, walking in a circle within this vector field, how much work is involved. And we'll use integrals to actually do that. Maybe not integrals like you've seen so far. Maybe
Line integrals?
whole new types of integrals that you've never seen before. So you guys allow me, if I just simply Google search. Actually, I don't have any program names. So first, I do one. Guys, I'm not using a program here at all. I'm just simply going on Google, just Google searching images.
So that one, yeah.
That one's cool.
But can you guys appreciate that some of these vector fields look really basic? Like here, this might represent fluid flow. Oh, gravitational pull. Actually, isn't it a little opposite of that though? Because I think the vectors as they come
I mean, it would be the exact opposite.
Yeah, the magnitude vectors.
Okay, imagine if it was the exact opposite, then it'd be gravitational pull.
What does this one look like? What do you mean hurricane?
Or
Oh, you mean
tornado or
tornado.
something like that, yeah.
Yeah, tornado.
Ah, okay, so maybe this is some kind of rotational vector field in 3-dimensional space. And we'll need to deal with those. For those of you who study a little bit of physics, what do I use as a word to talk about a whole new vector? How about just a whole line that goes through the center of the rotation?
Axis rotation.
Okay, or call it the curl?
Never heard of it.
Never mind, don't worry about it, we'll be computing curls all over the place next week. What other one can I grab? Ooh, this is kind of nice. You guys, can you see it or do I need to blow it up?
Blow it up. I think that's what he meant.
It looks nice.
It all got real complicated.
So you guys, check out how interesting this vector field is. I did not do this before class. I'm just looking at these for the first time. But notice how this point right here seems to be an attractor. I sometimes refer to it as a sinkhole. sort of like a hole in a sink where all the water's coming in, going down. Or maybe you can think of a black hole, same idea.
Why are the arrows curving?
Yeah, I haven't gotten there yet. I think that's a much more complex, interesting point in the vector field.
Looks like magnetic field.
It really does, because look at some of the arrows that are actually coming into that particular special point, so the other ones are wrapping around.
Well, it looks like there's like two actual, like, I don't know what to call them, like, circle thingies.
See, I disagree with that. I think that all that's going on here is that from one pole to the next, I'm attracting the particles.
Okay.
So I don't think in this particular image we're really looking at circles duplicated.
That kind of reminds me of like the Coriolis attraction. I mean, ignoring the two lines going in and out, like,
I can see that. I can see that. You guys, are there any other interesting ones on here? Let me check.
don't, that's not the one you want to click, just go back.
Thank you. It's been so long since I've used Explorer. I never use Explorer anymore.
So long to go
Go
up.
do the one above it.
The one above it?
Yeah. Oh, wait, up, yeah, that one.
That looks like,
What the heck is that?
reminds me of a fractal.
Oops, what did you do?
I don't know.
What is it?
That looks cool.
It's like an alien spaceship.
It's just like Ender's Game.
Ender's Game?
Deborah and I went and saw it yesterday,
Oh.
and the alien spaceships kind of look like.
Oh. I'm not sure what this is. I think what's going on is I've got level surfaces. Into each level surface, I've got an associated vector. When I'm looking at this image, that's what's going through my mind. But it does make it pretty good.
It kind of looks like tornadoes a little bit.
You're stuck on tornadoes.
It doesn't look anything like a tornado. That looks like the invading walkers from what's that? Yeah, War of the Worlds. That's exactly what I was
What
thinking.
does it say about it? Does it have a comment about it?
You guys have seen way too many movies.
It's the, what's it called, the Lorentz attractor, is that a vector field?
The what? No, but I can create a vector field describing the phenomenon. Sorry, you guys.
Lorentz attractor.
A what attractor?
So, Linda, what did you ask?
Oh, well, I thought I had a comment about it.
Yeah, let's go and take a peek. So Le Champ is a study for small caliber architects.
Oh,
That is so disappointing. You know, it's interesting on that note. A professor from the art department approached me last week. So he wants to create a big poster describing a certain phenomenon. And he doesn't know the math. He just wants a mathematician to, print on there the appropriate mathematics. He's saying when he's on a potter wheel, what do you call that thing? A pottery wheel? He says when he pops this goo on there, it's lopsided. It's not rotating symmetrically. So he just taps it with his hand, and whoosh, it just gets in the right position. It's nice and centered. So he wants to know the mathematics behind that. It's interesting you brought that up. So we're going to work on that mathematical model. You guys, let's see.
What's that saddle right there?
Saddle. Oh, right here. It looks like it's just an equation of a surface.
with the swirly thing above it to the right.
No, the other one, the other swirly there.
Oh, that's just like a really spooky book cover. You look up
That's
a
the
fractal.
trippiest vector calculus book I've ever.
I couldn't use a snap tracker.
Oh, okay. I mean, I really think we're just nerding out too much. And we haven't even talked about any math.
That one looks cool.
You guys in this section, I'm not going to talk about any real math.
Any real
It's not, no, seriously, just look at pictures and just talk about this particular problem. This looks really interesting.
If I just
So, are there any like math classes that are like an extension of vector calculus after this one?
not a Sierra.
No, well, of course not. But I mean, like at a university, does vector calculus go any further?
A lot.
Yeah.
And this is intimately related to a subfield of mathematics called complex analysis.
Okay,
Because just like a complex number, just back in trigonometry, you can also think of as a vector.
okay.
All the underlying mathematics is the same. You guys, this one looks really interesting. Can you see what's going on? Can you describe in words what's happening? Sorry.
Is that like Earth at the bottom of it?
Say it again.
Stuff is
Looks
exploding.
like Earth at the bottom of it.
Oh, I have no idea what it is.
Earth is exploding.
Could you just say something on the vector field? This looks really interesting.
It looks as z is decreasing, the magnitude is increasing, so it's looking like.
And anywhere in the x, y, z coordinate system, all the vectors are moving straight away from the origin. I can't hear you.
The origin.
I can't hear you.
The y-axis.
The
The
z-axis.
z-axis.
Excuse me.
Z-axis.
Sorry.
Very
I
nice.
described it with my hands.
And the further you go up with the z-axis, the greater the magnitudes.
The exact opposite.
No. Oh, magnitude, yeah, with the slant.
Oh, you mean magnitudes in respect to the z?
Yes.
Oh, okay. I thought you.
That was very nice.
Wait, were
That is.
the vectors parallel?
No, they were not vector. It was an example of a radial vector field. They're all going away from something. They just weren't going away from a point. They were going away from
It
a
looked like, so they are getting less and less steep as it went up. then.
Maddie, I don't know. The way I was looking at it, I think they were all parallel to the
They
x,
were.
y coordinate plane.
Okay.
Why do I keep closing that out?
You can go shift
you're
T
old.
over here.
I heard that.
I didn't say it quietly.
Don't you ever worry about, I'm the one that signs the letter grade?
Not the slightest. I mean, if I said anything like really hurtful or really mean, then yes, but not when I'm just joking around.
Okay, here's an interesting one. Just my first example, wasn't it? Like a radial vector field that's radially going away from the origin.
Oh, that's what that is.
I'm so glad I found a program that works.
What website is this?
I have no idea.
KevinMarshall.net?
Kevin
Or
Mehal.
KevinMehal.net, alright.
Now, you guys, notice what I just did. I rewrote it in this program. I interchanged the x and y with negative y and x respectively. Notice how this is basically a radial vector field, kind of rotating around a certain point.
The further you go out from the origin, the bigger the magnitude.
That's true. So it's like the swirling is faster and faster the further we get away from the origin. It's just a two-dimensional vector field, not a three-dimensional.
Can you put it in 3 dimensions?
I have no idea.
No, probably not.
This one seems to only have x and y variables.
Just type into Google three-dimensional vector fields.
Yeah,
Probably
yeah.
find something.
You say later.
Allow. You shouldn't use Internet Explorer too.
Yeah, I love Explorer.
Oh, I hate it.
The problem with Chrome is it's like its pop-up blocker is so good that it just blocks everything. Like, you know how hard it is to illegally download videos using Chrome? Like,
It's not hard at all to download videos on Chrome. It just opens up in the bottom and you just click on it. And
well, obviously I didn't know that.
Yeah.
Why don't you use Chrome instead?
I'm frozen.
you should take Internet Explorer and put it in your recycling bin, and then go and use Chrome or Firefox. That works. Yeah.
Because the website doesn't support it. I froze my computer yesterday downloading Prometheus off Pirate Bay.
Oh, why would you watch Prometheus?
Because memory told me it was better than it actually was. The first time I watched it, like I was really stoned, and I thought it was just like amazing. Did you waste that half an hour?
Do you ever wonder why a person would like run in a straight line from like a cylindrical object?
For like 100 feet. It's like this.
All you
wide.
have to do is just jump off to the side, and you'll be fine.
Oh wow. It sucks that your standalone can die.
Yeah.
Where have you never been? Being. Don't even bother. I mean. No, it's like every time I like search still like $1 billion corporation.
No, I know, I'm kidding. Sarcasm.
I'm not sure how that's physically
What?
possible.
Ooh, Wolfram
I don't
output.
think I've ever used AOL like, in my life.
Yahoo Answers, that's easy.
Yahoo Answers ever does it.
I want to get on to.
They updated it. They updated it like a few months ago.
Really?
Yeah.
Yeah, Firefox is bad. It just doesn't have all the neat things. Like with Google Chrome, you can download a pop-up blocker that makes it so you don't get any ads
What's
ever.
with you and pop-up blockers?
Dude, I don't like
And then you can't pirate stuff when you do that.
That's why I
Okay,
also,
guys, I can't find anything more neat, I don't wanna waste more time. Oh, there's a nice one.
that's pretty cool.
What does that say to you? Explosion. Another radio vector.
That does not say explosion. Because like an explosion, it would get it'd get faster and then smaller.
Well, we haven't suppressed it.
Whoa, 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 hold it. What did you say?
It's the magnitude.
No, it would be accelerating as it's going away from these.
Is that really what's going on in the universe?
Yeah, we're.
Yeah, it is. I mean, we are having that affect the universe, so you can't just say an explosion doesn't operate that way. I think you're thinking in terms of Newtonian physics.
Well, you can also
I
describe
thought the
it
universe
as
was slowing down.
Yeah, I thought the universe is cooling and slowing down.
No,
Like,
it's
not.
It's expanding, it's accelerating.
You know, I just watched the Stephen Hawking documentary of Benedict Cumberbatch, and they said
They said what?
it was a really good document. They said that it's like the leftover astral radiation, blah blah blah. It's cooling down, so it's slowing down, right?
Well, it's cooler and slower than it was at the beginning, but it is accelerating from.
What? How can it be cooler and slower than it was at the beginning and getting faster?
I'm not saying it's
How does
faster
that
than it
work?
was at the very, very beginning, but it is accelerating. We are expanding. The universe is expanding.
That's why we've deduced there's antimatter, because of the acceleration of the universe. The acceleration expansion.
Isn't that dark energy, what they call it?
Yeah.
That's same thing, yeah.
But we have to find some kind of principle that actually allows it to happen. All right, you guys, I'll come back. I'll stop playing with pretty pictures.
I do recommend seeing that, like, it was a BBC thing.
Prometheus?
No.
Just, so we're saying that the farther you get out, the faster it's accelerating. Wouldn't there used to be some sort of thing that, theory, maybe super old, because I've heard it forever ago, with like the mushroom effect, where it might come back together eventually?
that has to do with,
That was like the basic premise.
basically, it wasn't accelerating like that.
Yeah, exactly.
Yeah.
Maddie, it depends on,
That was forever
if
ago.
you're gonna read a book, it really depends on when it was produced or written, because the theories keep changing. It's just the most recent data we've received from the Big Bang is suggesting the universe is expanding at accelerating rates. Now, did the Big Bang occur because there is an implosion? It's debatable. I think most scientists would say today, yeah, that was the case. And therefore, the Big Bang really is not the initial start of the universe. There was something there before that contracted. Well, good question. Why did it? I don't know if the theoretical physicists agree with that.
Wouldn't this acceleration have to be increasing also because the farther you get away, the less gravitation because the radius is larger?
That's why they're contemplating all this business with antimatter, dark matter. There's got to be something there that's allowing the acceleration to occur, because matter can't possibly destroy that. Anyway. Oh, it's very fun stuff.
When we all finally go to 4 years, you have to worry about shit like that. It's just like jeepers like that. That was actually me attempting to be respectful.
Attempting. I see. What if I'm traveling on a circle? What can you possibly say about a radial vector field at this particular point right here? Call the point and come along. What's the associated vector with it? If it's really a radial vector field emanating from the origin, what is the corresponding vector in the slope field? No, you're thinking too much.
That way, up.
That way up. It's going to have components.
X,
I agree. What do you think you could possibly say about the normal vector?
Yeah, it's just gonna be the tangential.
Yeah, I don't give it to me.
What?
Give it to me. Negative y comma x. Do you think those vectors should be orthogonal? Yeah, it should be. Prove it.
Does it matter which way we go with that tangent on the circle?
You know, good point. No, I should. If I gave you the orientation by tracing out the curve, it should. And I didn't do it. But if I go in the counterclockwise direction, then I am correct. As opposed to the clockwise direction.
Didn't you imply they were orthogonal when you said you were drawing a normal vector?
Yeah, I know, I'm being silly. But the reason why I asked the question, you just lost your memory. You forgot about that.
Okay, well,
Look at these two vectors, how can you verify they're orthogonal?
we look at the slopes, we know that that perpendicular lines, for example, and the same is true with vectors, have negative reciprocal slopes, so.
And that's actually how I came with the negative y-axis. I agree with that. But now I've got the vectors on the board, how can you show me that those vectors are orthogonal? Look at the dot product. Clearly the dot product is equal to 0. I know I'm being silly. I say the same darn thing in a different way. Suppose I have this function. I'll change the letters. How about phi? It's a function of two variables. Do you think you can come up with a gradient vector for phi? What is a gradient vector? Oh, you guys. 2x plus y? 2xy? Oh, comma. And then it'll be a... In other words, this is a vector.
Sure.
So, if I have a vector field that can be expressed as a gradient of some scalar function phi, I will say that phi is a potential function.
Wait, say that again.
What's what?
What's, is that like an E or F?
Oh, you mean this is right here?
No, that thing down there. Yeah.
My self-esteem's going down the drain.
So this is the gradient function is equaling that?
Can I rephrase that?
Yes.
I'd rather you refer to this as gradient vector field now. And so gradient vector field is simply a vector field that has a quality that is a result of the gradient evaluated on some scalar value function. And I will sometimes refer to that function phi as my potential function. Today in class, I'm being goofy, I'm being silly, I'm just giving you a vocabulary. Who the heck really cares? But starting next week, we're going to care. Being able to come up with a scalar function like phi is going to allow me to use a whole new version of the second fundamental theorem of calculus, just in higher dimensional space. So it will be important. Today, I'm just throwing out some vocabulary.
So you're going to find a scalar factor?
I'm saying a vector field is a gradient vector field if you can find a corresponding scalar function. Can I say it differently? If a vector field has this quality, I'll subclassify it as being conservative. So having a vector field that's conservative simply means I can find some scalar value function whose gradient really is my vector field. And I will give you tools coming up soon on how to actually find that potential function from a gradient vector.
That's because that's the slope, right? So when you're drawing your lines, it's just like the slope fields, because your gradient's the slope.
You know, it really is the same thing, I agree.
So you're drawing the slope of the function at that point, right?
I agree, at all the points. For those of you who studied Math 33, you really use the same idea when you solve exact differential equations. Remember the first order differential equations? Some of you can handle
Say
that.
that one more time, the scalar value function.
I'm saying a vector field is conservative if you can find some scalar function phi, for which the gradient of that scalar value function is going to be nothing more than your vector field. And I will give you techniques on how to actually find it. But those Math 33 graduates already know that technique,
Be on the top, you mean?
to find the function phi on top.
It was conservative.
So a vector field is conservative simply means that it
Did
is
you
equal
write
to
that sentence, please?
a vector field. Eric, so far so good?
You're okay, you're okay.
No,
Oh,
just
it's
checking.
your field.
It's conservative. If there exists a scalar value function, say phi, when you look at the gradient of that scalar value function, I call it phi, it is your vector field. This function phi is called a potential function.
Beginning to sound a lot like DNF from AP Physics.
Oh, absolutely. And we'll talk about the amount of work required to go through a certain type of vector field and how we can determine, in that case, if I get conservative.
What is potential function? What is that?
It's a whole new word I made up out of thin air.
Okay.
And it simply represents a function whose gradient vector is equal to my vector field.
Okay.
So if I started with a vector field f bar, all of a sudden I can find some scalar value function phi whose gradient is really my vector value function, my gradient, my vector field. Then I will refer to that function phi as my potential function.